So we have talked about conservation of energy and how it relates to gravitational potential energy and kinetic energy and spring energy and different forms of energy. But now we need to talk about absolute gravitational potential energy. It is different from how we've been talking about it, gravitational potential energy, in the previous video. So let's just look at some similarities first. Remember, if we had a mass just sitting here on a desk and we raise that mass up, we have changed its height, and changing its height would change its gravitational potential energy. If we move it sideways and there's no change in height, it doesn't take any work or any force to move it sideways, so no change in height, no change in its gravitational potential energy. And if we just keep on moving it sideways, it shouldn't have any change in height, so no change in gravitational potential energy. We haven't done any work moving it from here out there. Or have we? Well, we haven't, but if we move that mass so far that it actually goes out the window and now is at a much greater height, it has energy, more energy than it did a moment ago on a relative scale. So we didn't clarify with this, we just called it gravitational potential energy. But now we need to refer it as relative gravitational potential energy. It doesn't tell you what the gravitational potential energy is. This equation just tells you by how much it has changed. So changing from here to here, the height, changes the gravitational potential energy. But we want to come up with what the gravitational potential energy actually is, not by just how much it has changed. Another example here is if we had a bowling ball sitting on the ground here. If it's sitting on the ground, it's at no height, so you might think that the gravitational potential was zero. But what if a sinkhole opened up and now all of a sudden it is at some height and it could fall? Again, we're talking about relative gravitational potential energy. And this is where I'm going to introduce this idea of what's called absolute gravitational potential energy. Instead of U sub little g, this is U sub big G. And there is a difference. And there's an equation to calculate the change here, but this equation is going to just calculate what it actually is. And we need to do it on an absolute scale. So you're probably familiar with Celsius versus Kelvin, that 0 degrees Celsius is just when water freezes, but you can have negative numbers. And then we have the Kelvin scale, which shifts the whole scale so that 0 is the absolute bottom. You can't go past 0. So when the ball was sitting here on the ground, it seemed like it was right here at 0, but it wasn't the absolute bottom. There was a place you could go past. And you might think that the bottom, the absolute bottom, would be the center of the Earth, but there's another absolute place that we can think about that's going to work a little better for us. I'll get to that in a moment. This equation here only calculates the change in the gravitational potential energy, not what the actual energy is. So we looked at this example in the last video where I had a brick and I changed its height from here to here. And now what we want to do is look at that with the Earth in the picture. So that would be, not quite to scale here, and well, okay, it's still not to scale, but a better scale. But the thing is, if we had a really big change in height here, we, in using this equation, pretended that the acceleration of gravity was constant. That we just plug in 9.8 and it tells us this. Well, that's how much gravity there is here, but that's not how much the acceleration of gravity is way up here. That when we move at great distances, the acceleration of gravity gets less and less and less. So when we're using this equation here, it really is moving small enough distances so that there's no real appreciable change in the gravitational acceleration. So it really is a constant, relatively constant, moving it from the bottom floor of a building to the top floor of a building. Yes, it's a little less, but in this equation here, we pretend that the acceleration stays the same. But to do this on an absolute scale, we need to deal with not accelerations that are changing, but constants. So we're going to talk about, instead of u sub little g, which changes with height, we need to talk about u sub big G, and that is the universal gravitational constant. And we talked about that when we were doing circular motion. And that constant is 6.67 times 10 to the negative 11. All right, before we get into that, I need to do two examples that are pretty easy. And then the third example is going to be a little more complicated, but it will allow me now to explain how we use this new equation. So we want to find out the work that was done moving an object from 1 meter to 4 meters. So we're going to move it from this distance to this distance. And in this example, the force was a constant 0.5, like 0.5 newtons. Well, we have to think about area under the curve. Well, if work is the force times the distance. It had this much force over this much distance, that times that, well, that's just the area of that rectangle. Although it's not measured in like square feet or anything, it's Newton meters, because this was measured in newtons and that was measured in meters. Okay, so we can find the work that was done by taking the average force times the distance. So if we moved from 1 to 4, we subtract those, and that's the distance moved. 0.5 times 3 is 1.5 joules of work, moving it from here to here. Okay, that was an easy example. Let's look at this one. Let's say that we varied the force, that we pushed with 1 newton of force when it was at 1 meter, but by the time we got to 4 meters, we were only pushing with 0.25 newtons. Okay, so force of 1 newton up there, force of 0.25 down there, but still it's the area under that line. We say the area under the curve. What we want to do is find the average force, because if I can take the average force and multiply by the distance, that'd give me work. Well, because it's a straight line here, the average is just going to be a simple average. Taking 1 plus 0.5 and dividing by 2, we would get a number there, but the area under that, this average force times the distance, would be the work that was done. Average force times the distance, this time it was 1.9 joules of work. And I want to also point out that the area of this green shape, this trapezoid, will equal the area of that red one. This little triangle here would fit into that little piece there. So the area under that green would be the same thing as the area of the average force times that same amount of distance. All right, now we're going to get to this example. Let's say that the force varied not in a linear way, but as a power, where it's proportional to 1 over the radius squared. So that shape is going to curve like this. We want to find that at this distance, it had this amount of force. If it's 1 over the distance squared, 1 over 1 times 1 is the same thing as 1 over 1 squared. Okay, and so the force there is 1 right there. Over here, at 4, it's 1 over 4 squared, but that's the same thing as 1 over 4 times 4. Okay, or that number there, 0.0625. What I want to do now is to find the area of that shape. And you think, what? Well, it's the same thing as finding the average force here times that distance. Now, we can do this, and this isn't going to be very satisfying here. This only works for when you have an equation of 1 over a number squared. So like we had 1 over 1 squared and 1 over 4 squared. We can find the average if instead of taking 1 over the distance squared, you take 1 over the distance when it was here and then multiply by what it was over here. So 1 over 1 times 4. Instead of 1 times 1 and 4 times 4, you take 1 times 4. And I know that's not very satisfying. It requires calculus to actually make sense of that. But if you get the answer, it's going to be 0.25 because that's 1 over 4. There's the calculus if you would like. Most of us haven't had calculus yet, so we'll pretend we didn't see that. But we can find the average force when it curves like this as an inverse square by taking 1 over, instead of the radius squared, you take it 1 over one of the radii times the other radii. Okay, so the work is going to be the average force times the distance, and this time the work was 0.75 joules. Okay. All this slide tells us is how to find the average force. So now let's do that here, because the force here is very different than what the force was up here. And we can use the universal gravitational equation to calculate the force of gravity up there. It's the universal gravitational constant, the mass of one object, our little barbell, the mass of the other object, the Earth, and how far they are apart from each other. So r sub a is the radius here at point A, and that's 1 over the radius squared. If we move that thing down to here, it's lost some gravitational potential energy. So because it lost gravitational potential energy, the gravitational field is doing work on the object. If we did work on the object and pushed it from here all the way up to up there, we would have given it gravitational potential energy. But because gravity is doing the work, going from here to here, it's losing gravitational potential energy. So when it's down here, there's going to be a different amount of force. And we can calculate what that force is by just plugging in this new radius. It had some distance up here, it had different distance down here, and that's how much force it is here, that's how much force it is up there. We would like to calculate how much work would be done moving it from here to here or from here to there. The amount of work done would be the same thing as the change in energy going from here to here. All right, so here's that thing I was talking about in the previous slides, that we can find the average force. The actual force at one spot was 1 over that distance squared, and over this distance it was 1 over this distance squared. But we can find the average by plugging in one distance and then the other distance. That's the average force between here and here. And the distance, we are going to be consistent with the final distance minus the initial distance. So if it started here, that was the initial, and then it ended up here, that was the final. So we're going to subtract those two things, and that's going to be the distance moved. So this is this number times this number divided by this number and times that number. But multiplication and division can be done in any order. So I could take this times that times this and then divide by that, and it'd be the same things up there. When I have numbers with like addition or subtraction in the middle here with parentheses, if I had a number here, you could distribute that number to here and here. Similarly, a number down here can be distributed to here and there. And that's what I'm doing here. I'm taking that number and I'm distributing it to here and also to there. Well, if I have an r sub b on the top and an r sub b on the bottom, they can cancel. An r sub a on the top and an r sub a on the bottom, they can cancel. So that's what we get. This would be how much work gravity would have done moving that mass from here to here. I just have to know the gravitational constant, the mass of the dumbbell, the mass of the Earth, how far it was when it was way up here, and how far it was when it was way down there. That would calculate how much work was done when the force varied. All right, I'm a little afraid here, but let me click forward here. And this is a calculus idea again. I'm not trying to teach you calculus, so I'm going to try to do it in more understandable ways. But we say the limit as r sub a goes to infinity. So, wow. Instead of moving the object from here to here, let's move that object all the way up there, really, 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 really far away, infinitely far away. And that is going to be our absolute distance, the point we can't go past on an absolute scale. So if we figure out how much work gravity would have done bringing it from infinity way up there to down here, that's how much work it would have had, or the change in energy going from infinity to here. Okay, so we treat this number here like a really, really, really big number. And if I take 1 over a really, really, really big number, that fraction is going to become 0, or it's going to get closer and closer to 0. So this equation here simplifies down into this right here. Just that term disappeared. What that tells us is if I just plug in this distance, how far we are from Earth here, that's how much work gravity would have done bringing it from infinity to right there. And that simplifies down here. I'm just going to put this whole term, I'm going to multiply this term in, and we get the negative there. So that's how much work it would have taken moving it from infinity to there. I have r sub b here, and I have just r sub, I just have r, there's no subscript. So over here, we didn't have to clarify between an r sub a, which was up here, and an r sub b, which was down here. This one went off to infinity, and it disappeared out of our equation. So we're just going to see how much work it would take bringing it from infinity to this distance, just r. So I'm plugging in just a number there. The amount of work that gravity did is going to be the change in its gravitational potential energy on an absolute scale, because this number does not change. Okay, so this is called absolute gravitational potential energy. And we need to talk about that negative a little bit. That negative is just because this is how much energy the object lost coming from infinity to right there. Okay, now let me move on to the next slide here. That's the same thing as we just had. What students don't like about this, and what may not make sense initially, is that with the other equation, mg delta y, for the u sub little g, the bigger the distance, the bigger the gravitational potential energy. But here, the r is in the denominator. So as this number gets bigger and bigger and bigger, the resultant gets smaller and smaller and smaller. So when you're at bigger distances, that number's smaller than when you're at closer distances, that number's bigger. We don't like that. Okay, it seems like the further away you go, the more energy you should have. But here's what's happening. This is how much energy it is lost coming from infinity. So if it came from infinity to right here, it's only lost 2,000 joules. If it comes from infinity to right here, it's lost 8,000 joules. It's lost more energy. That negative is important. It's not ever very interesting to just say how much energy an object has. It's only interesting when it changes its energy. So we always find the change in something by taking the final minus the initial. So we have negatives here, but let's see how those negatives work out here. If I move the object from here to here, we take the final minus the initial. The final was minus 8,000 joules. The initial was minus 2,000. But 8,000 minus a minus 2,000, that's going to be plus there. We get negative 6,000 joules. And the change was negative 6,000 joules, which means it lost 6,000 joules of energy. The negative means it lost it. So yeah, going from here to here, it's going to lose 6,000 joules of energy. If I go from here to up there, we're consistent to find the change as final minus the initial. So the final was 2,000, the initial was minus 8,000, 2,000 or negative 2,000 minus a minus 8,000 is the same thing as negative 2,000 plus 8,000. You get a positive answer this time. So going from here to here, the change was positive. So hopefully that makes you a little more comfortable with having negatives here. All right, the object gained 6,000 joules of energy. Now this is the space shuttle launching off in Titusville Florida. And we notice that it's kind of going off at an angle here. In fact, if that was launched at night and we did a time lapse, it looks like it's daytime, but it's just a time lapse. It was here, and now it's all the way over here. It's so bright because the lens on the shutter on the camera was open the whole time. But you can see that the shuttle goes up and then angles off in some direction here. Well, what direction? Is it north, south, east, or west? We always launch to the east. Here's why. So here's the South Pole here, and we have the Earth rotating around. The Earth is rotating to the east. So if we want to put a rocket or a satellite in orbit, we just launch it in the same direction. It's already moving, and it saves a lot of energy. If you launched it in the other direction, it would take a lot of energy to bring it to a stop, and then a lot more energy to get it going fast enough to go around. All right. So here's the big problem we want to work on. How much energy is required to put a satellite into geosynchronous orbit? So when the Earth rotates around like this, the satellite is rotating at the exact same speed. Okay, but when that satellite is here on Earth, it has some kinetic energy. It's moving. And it has some gravitational potential energy because of its distance from infinity. And we want to move it from here to up there. And up there, it's going to have a different amount of kinetic energy and a different potential energy. All right, this was an equation called Kepler's third law, relating the time it takes to go around and how far it is. I won't derive that for you, but I did do that at one point for you. And this is the equation I developed for you today. So let's say this is the mass of the Earth, this is the mass of the satellite, and this is the radius of the Earth. The first thing we're going to do is find out what the radius is going to be when it's way up there. So what we can do is plug in this time, this 86,400 seconds. That's how many seconds are in a day. We plug that in here, mass of the Earth, and we can find out how far we need to place that. We've done that problem before. So that's going to be the radius when it's up there at that distance. So to find out how much energy we need to give the satellite, we need to figure out how much energy it has when it's here and how much energy it has when it's up here, and find the difference in energy, and that's what we need to supply it to get it up to that place in space. So the total it has at the surface, it has some absolute gravitational potential energy, and it has some kinetic energy. Now, I'm not going to plug in all these numbers for you. I'm just going ahead and give you the answer here, because the numbers are kind of big. But I do want to remind you that we can calculate what the velocity of that is right here at the surface by taking the circumference, which is 2 pi in the radius, divided by the time it takes to go all the way around, which is this many seconds. So just distance divided by time is how fast it's traveling right here. So this is the absolute gravitational potential, and this is its kinetic energy. So when I plug in the radius of the Earth and the mass of the satellite, this is what I get for the absolute gravitational potential energy. It's negative. And this is what I get for its kinetic energy. Notice this is 10 to the 11 and this is 10 to the 8th, a much bigger number here. And that's what I get when I add those two together. When it's up here in space, it has a different velocity because it's at a much different radius. This is the radius, or the circumference that it has, and it's still divided by the 86,400 seconds. So it has a lot more gravitational potential energy and a lot more kinetic energy, but when I add those, this is the number I get. So this is how much energy it had on Earth, this is how much energy it had up there in space, and when I find the change, you take the final, this number here, minus the initial. This final minus this negative initial is the same thing as adding those two things, and the difference is this number here for the number of joules. Okay, that's why we have to be careful with that negative. So just kind of some applications of this. If this is Earth orbiting the Sun, when it's in its elliptical orbit, nowhere near as elliptical as I've shown it here. I've highly exaggerated the eccentricity of its orbit, just how squashed that circle is. But when it's here, it has a lot of absolute gravitational potential energy and not as much kinetic energy. And when it's here, it's closer, so it doesn't have as much absolute gravitational, but it has a lot more kinetic energy. It's going to be going faster in through here. Okay, and that is what's known as Kepler's second law of planetary motion. I don't know how he figured this out, but if you take on equal times, so like going, say, 2 months of time from here to here, and 2 months of time going from there to there, Kepler's second law says the area of this sector and the area of that sector are going to be equal. It's moving faster here and slower there. All right, planets sweep out equal areas of the sector in equal times. All right, that's it for absolute gravitational potential energy. I do want to briefly talk about mechanical energy. But mechanical energy is just the sum of its potential energy and its kinetic energy. It's kind of lumped together. So the mechanical energy is this, if we're just talking about movement in the classroom, small movements where the gravity is about the same, or if it's large distances, then we'd have to use the other equation we just developed. Okay, but mechanical energy is just the energy associated with the position and the motion of an object. With that being said, we want to talk about systems. We often like to talk about what is the system? What are we referring to? So if we have these two, I'll back up. If we had these two soapbox racers and they're racing down the hill here, we know that as they go down the hill, they lose potential energy, they gain kinetic energy. But let's talk about it in terms of systems. What happens to the mechanical energy of the car-Earth system? So we're looking at the car and the Earth together as one thing. Well, the Earth pulls the car down, the car pulls the Earth up, but these are forces that are inside the system. So the force between the car and the Earth is an internal force. Potential energy is transformed into kinetic energy, but there was no change in the mechanical energy. It remained constant. If I look at just the car, I'm solely focused in the car, I'm not even looking at the Earth. As I look at the car system, Earth is pulling the car down, but that was a force that came from outside the system. So the force the Earth exerts on the car is an external force, and that's doing work on it, increasing the kinetic energy of the system. And because the kinetic energy increased, so did the mechanical energy. Because when we look at just the car and we're not even looking at the Earth, potential energy is irrelevant. We don't even see where it is in relationship to the Earth if we're solely focused on the car as its own system. So if there is no potential energy that we're looking at, just an increase in kinetic energy would also be an increase in the mechanical energy. Let's look at it like this. If we have the car-Earth system, or just the car, as the car falls down, its potential energy was replaced with kinetic energy, but the mechanical energy remained constant. Here, it started out with no mechanical energy. We're not even looking at potential because we can't even see the Earth. We're solely focused in on the car. But we just see the car going faster and faster and faster. So the kinetic energy increased, so the mechanical energy would have also increased. Say we have a sled hill or a grassy hill, and this person's going to slide down from the top of the hill to here, or from the top of the hill to there. Which situation would have the greater change in potential energy? Well, if they've dropped the same distance and the gravity is the same in both cases, they'd have the same change in potential energy. Which would have a greater change in kinetic energy? Well, you can imagine that this was going on the snow, so it's very little friction. They'd be going a lot faster here than they would over here. So there'd be a lot bigger change in kinetic energy for this person than for this person. The snow person would have a greater change in the kinetic energy. Okay, now which one would have a greater change in the mechanical energy if we're looking at the person and the Earth as its own system. Okay, so we're looking at, we do include potential energy, which would have a greater change in the mechanical energy. Well, that's going to be this one, and that's a little surprising. Here, if this was no friction, there would have been no change in the mechanical energy. It would have been conserved. Okay, but here, because there is friction, some of the mechanical energy was transformed into heat through friction. Not as much friction here, not as much heat. More friction, more heat. So it really is just that more of the mechanical energy was transformed into heat. So the grass had a greater change, meaning it was a greater loss. That's mechanical energy and a little bit about systems.